Okay, hello everyone, I'm Sanjeev. I'm a master's student in the Material Science and Engineering department. I work with Dr. Dev Chidambaram, and my master's project is on the electrodeposition of terbium using molten salts. Now today I'll be talking to you all about, first I'll let you know the motivation for my research, give you a brief introduction on what rare earth metals and molten salts are, talk briefly about electrodeposition and my master's research then. There are not much results there. I just started doing my research, so you're going to be hearing a lot of introduction there. Okay, so why am I actually pursuing this research? Pyrochemical reprocessing of nuclear fuels is a very important step for the advanced nuclear fuel cycles. Right now, in the nuclear fuel cycles, our end product is fission products plus uranium and then transuranics. Transuranics are those with atomic numbers greater than 92. They have very high radioactive half-lives. So dumping them in, like trying to get rid of them in geological repositories is going to cause a lot of radioactivity for a long time. These also include plutonium, which is a fuel for fast reactors, for nuclear fast reactors. So lanthanides basically, okay, so basically right now what recycling process are applied in the industry is that all of these end products are taken and dumped into fast reactors, and plutonium is a fuel for them, and plutonium burns by undergoing nuclear fission, and the heat produced from that is used to burn all the other elements present there. But you also have a lot of neutron poisons in there, which actually absorb neutrons but do not undergo beneficial fission reactions, and so that's detrimental to the efficiency of the entire process. So my research comes in here. What I'm trying to do, terbium is also a neutron poison. What I'm trying to do is extract terbium out of there before they're actually put into the fast reactors so that we improve the efficiency of the entire process. Now, you might ask the question, like, why don't you use simple aqueous solutions for electrodeposition? If we're using pyrochemical reprocessing because it has the following advantages. The first one, process simplicity. You simply take your end product, put them in a furnace, melt them out, try to extract all the metals you want out of there, or you can, by electrodeposition. The rest of them, again at room temperature, they're a solidified mass, so you just have to dump them in canisters or repositories. And the volume of the test solution, when you're using aqueous solutions, you're going to be looking at increasing a lot of the test volume because you have to basically react them with acids first. So when you want to react the huge amount of leftover end product you have with acids, you're going to have to use a huge volume of acids there. And then radioactivity. Now when you do pyroprocessing, you just basically left with a huge ceramic block at the end of the recycling process. So you don't have any seeping through like you could have in when you use acids. You have a lot of radioactive toxic waste which could seep through your canisters, and that's a huge problem. Now, aqueous solutions was also used actually many years back for preparing nuclear bombs. You selectively could leach out only plutonium, and it was specifically used for creating nuclear bombs. But when you use pyrochemical reprocessing, you're looking at recovering all the lanthanides and the actinides present there. So yeah, that's the motivation for my research. Now, rare earth metals. The rare earth metals consist of lanthanides with atomic numbers 57 to 71. Also includes terbium in there, which is a heavy rare earth metal, atomic number 65. I'll show you on the, here. You see lanthanides here. Those are all the lanthanides, and the actinides are here. The transuranics I was talking about is from 92. You can see from atomic number 92 and above till 103, they're all transuranics. And plutonium is right here, 94. And terbium is here, 65. Okay, and scandium and yttrium are also included, scandium and yttrium here. They're also included in the lanthanides because they're basically found in the same minerals and they have similar chemical properties as lanthanides. Heavy rare earth metals are really difficult to extract due to their high oxygen affinity. You won't find any of those heavy rare earths existing in their elemental form, in their pure elemental form in nature. You always find them as oxides. And so because of this problem, you have to find a suitable molten salt which has a much higher negative reduction potential than the metals you're trying to actually electrodeposit out, so that you still have your media intact and you actually extract out only the metal of your choice. Molten salts are salts which are basically solid under standard conditions, and at elevated temperatures they'll melt and they conduct electricity then. Molten chloride salts are generally used as baths for pyroprocessing of nuclear fuels, alloy heat treatment, surface modification of alloys, etc. And molten fluoride salts are used in the Hall-Héroult process for commercial production of aluminum. Aluminum is produced only by this method right now. So what is electrodeposition? It's a process that uses electrical current to reduce cations of a desired material from a solution and coat that onto a conductive substrate surface. Now, I'll just give a couple of definitions here. Cations are positively charged ions, anions the negatively charged ions. Anode and cathode. Anode is your positively charged electrode and cathode is your negative electrode. Now, electrolyte is any compound that in solution or in its molten form conducts electricity and is electrolyzed by it. Now, electrochemical cell, you basically have two types of cells. Show you here. First one is galvanic cell and the second one is electrochemical cell. The first one is when you have a spontaneous chemical reaction occurring which induces the flow of electrons in the external circuit, so producing electricity. You have spontaneous chemical reactions producing electricity. In the second one, you have an external power supply which actually supplies electricity to your salts, and you induce chemical reactions by supplying this current. My master's project is first to achieve the electrodeposition of terbium from terbium chloride in lithium chloride, potassium chloride eutectic melt, then qualitatively and quantitatively determine if I've actually electrodeposited terbium, and efficiency evaluation of the entire process. Now, the electrolyte I'm using is LiCl KCl eutectic melt, as I mentioned before. The cathodes, tungsten or stainless steel. I'm mostly using tungsten because that seems to be giving better results. And anode, constantly using graphite. The melt temperatures for my experiments are 600 to 650 degrees Celsius. And all the experiments are conducted inside a glove box. You have a contained environment. There are very low moisture and oxygen contents. Now, terbium, as you can see here in TbCl3, exists in its +3 valency state. So you require 3 electrons to reduce it to its elemental form. And the competing anodic process is chlorine gas evolution at the graphite anode to maintain charge neutrality. Terbium deposition has been tested at different currents, 20 milliamps and 500 milliamps. We actually also recently tested at 1 amp. Don't have the qualitative and quantitative results for that yet. For qualitative determination of my experiments, I use electron dispersive spectroscopy. Now you can see here the Tb, the elements noted as Tb, there is terbium deposited there, and tungsten, W is tungsten, which was my substrate, which was my cathode, on which I was depositing terbium, and the rest of them, nickel, magnesium, aluminum, are trace impurities present in there. For quantitative determination, right now I'm using XPS, X-ray photoelectron spectroscopy. The peaks here, the first two peaks here are terbium peaks, and this one here, this is also terbium. This peak is related to tungsten, that was my substrate, the carbon and oxygen peaks. You're going to find them anywhere. And you can see the atomic percentages here. So basically it calculates, not only gives you a qualitative analysis of what elements you have there, it also calculates the area under the peaks and tells you how much atomic percent you have there, and you can actually rely on this data for quantitative determination. So I have about 32.1% of terbium on there. Not so good, but I'm trying to improve the process. And for efficiency calculations, using Faraday's first law of electrolysis, you can calculate the theoretical mass to be deposited when you apply a current for a particular time. So this is the simple equation here. This is the mass of whatever metal you're trying to deposit. I is the current, T the time, M is the molecular weight of the metal you're trying to deposit, F is the Faraday constant, and Z is the valency state of the metal ions you have in there. So after you got this, you calculate your current efficiency where you have the actual mass you deposited experimentally. The ratio of that to the theoretical mass you calculated from here, currently it's just the maximum I've gone up to is 30% efficiency. It's not much to say, but I have to improve the process a lot. Future work I'll be doing is achieve up to 88% terbium deposition. So we'll be done sequentially. The first step would be to run a constant current experiment for about 2 hours, then remove that cathode, wash it, and then do qualitative analysis. Make sure I actually have terbium on there. Measure the weight increase of the cathode. Now when I measure the weight increase, it's going to be directly coming from the terbium I've actually deposited there. After I've used the same cathode and the same salts which I used previously, and redo this experiment and try to deposit more onto my cathode, and I keep repeating this till I find at least there's 88% increase on the cathode. So that will tell me that I've deposited at least 80% of what salts I had in there initially. Okay. I'm also looking to improve the efficiency of the process. Thank you. Any questions?
Do you think you'd pull out other lanthanides in that process from spent nuclear fuel? Or any other things if you're going to that high potentials?
Yeah.
You just get terbium?
Actually, they have really close reduction potentials. So yeah, we could pull out other lanthanides too. But that should not be a problem because you're basically trying to improve the efficiency because all the lanthanides, any of the lanthanides present there are neutron poisons, the isotopes present in there. So the more you get out, the better, actually.
I might have missed it on the slide. You're getting 30% roughly efficiency?
Yeah.
What's the other 70% of the current due to?
I have no idea right now. So, no, I haven't figured out how much the over potential for the system is yet. So there's a lot of current getting wasted in that. And you have to actually figure that out. Okay, thank you.
Thanks.